Here what is happening, the radius keeps on increasing from r0 to capital R. So if we plot a diagram between R and V, what we are really going to get is something like this. This asymptote here is nothing but the y is equal to r naught line, and this here is capital R. At this point where it touches here, hopefully this is not going to be an asymptote, because we will be having a finite velocity of v naught at r naught. So this is how our velocity profile diagram will look like. The velocity lines being of this sort. Now let us consider something else. Let us consider the force here. So what is the force required to move the rod? With constant velocity v naught. So if we consider the free body diagram of this cylinder, we need to apply some force which will balance off the viscous force acting on this cylinder. This is what we require. So the viscous force will be equal to the applied force. This is going to be eta times area of contact or surface area times the velocity gradient at r0. The velocity gradient, as we found out earlier, we got this as dv by dr being equal to c by r. So the velocity gradient at r equal to r0 will be simply c by r0. Now we will replace the value of c that we got. C was found to be v naught divided by ln r naught by r. We replace it simply here. So what we get is Vg at r being equal to v naught by ln r naught by r times r naught. We put this here. For the area of cross section, we have the area of cross section of this cylinder, the surface area of the cylinder, and eta will remain as it is. So if we do that, we get the applied force to be equal to eta times 2 pi r naught L times the velocity gradient, which is going to be v naught by r naught times 1 by ln of r naught by r. This R naught cancels up with this R naught, and we are left with, let us simplify this in 2 pi eta L V naught divided by ln of R naught by R. This is the force which needs to be applied on this cylinder to make it move in this direction. Obviously, the viscous force will be in this direction. This is F viscous. These forces will balance off and thus will give you a constant velocity V naught. This solves our problem. Now let us consider another situation where our assumption of pressure gradient not being applied will not be valid. So we will be having a situation where we will be having a pressure gradient being applied across the pipe we are considering. So let's say we have this pipe. We have fluid flowing through from this side. And we have a pressure of PL here and a pressure of PR here. Note that PR is going to be less than PL. This can be achieved if we attach a pump on this side of the pipe. So the pump will try to push the water or whatever fluid you have within this channel through the channel. Let us say that this liquid has a density of rho and coefficient of viscosity eta. Let us say this radius is going to be R, and the length of this pipe is say L. This is the situation we are assuming. Let us also assume, like before, V increasing as R increases. Because of this, we will be having something of this sort. Say this is the force due to pressure. This plus, we will be having the same equation again, 2 pi R plus dr times L, velocity gradient at R plus dr, minus eta times 2 pi R. We are just considering any R here from the center line, into velocity gradient at R. This should be 0. Now we need to find what this force due to pressure be. This will be the pressure at any R, which is obviously going to be PL on this side, this being applied to a cylinder which is thick. By this, what I mean to say, if we look at this pipe from this side, we will be seeing this pipe like this, the cross section, and the two layers which we are considering like this. This distance is basically dr. So the cross sectional area covered by this portion of two layers is going to be 2 pi r times dr. Because we are considering an infinitesimally small distance between these two layers, it really does not matter if you directly multiply this dr to the circumference of the inner cylinder. So this is going to be valid. So the cross-sectional area of this annulus will be 2 pi r times dr. Say the pressure is P. Note that PL is the pressure at one end of this pipe and PR is the pressure on another end of this pipe. The greater pressure is on the left hand side and the lower pressure is on the right hand side. So there is going to be a pressure drop uniformly across this pipe. That pressure drop is going to lead to some arbitrary pressure within the pipe we are considering. So this is going to be, let's say, P. We will be later on seeing how the P varies.